Alzheimer's is the sixth leading cause of death and the most expensive disease in the United States. Over 44 million people worldwide live with Alzheimer's disease, but due to the costs and complications related to diagnosis, around 33 million people do not have access to treatment options, care, or support. This is because Alzheimer's diagnosis today is primarily conducted by neuroimaging techniques such as MRI and PET, as well as qualitative cognitive assessment such as the MMSC. These procedures are lengthy, expensive, and complicated, explaining why it may take up to 2 years for patients to get the care that they need. Synapto Engineering has developed a device combining open source OpenBCI hardware with machine learning models to attack this problem head-on. Our innovative device moves away from these current costly neuroimaging diagnostic techniques to a much more portable and affordable option, an electroencephalogram, commonly known as an EEG device that tracks and records brainwave patterns through analysis of electrical impulses within the brain. It has been proven that brainwaves in Alzheimer's patients are characteristically different than healthy patients, and we utilize this difference to engineer an artificial intelligence algorithm compatible with a portable EEG that has far-reaching diagnostic potential. Our device allows for an objective quantitative measure of systematic diagnosis rather than the cognitive qualitative assessments put forth by neurological diagnostic manuals. These qualitative assessments are only carried out after symptoms occur. Our device can observe a person's chance of getting Alzheimer's through the severity and change of brain waves. This, combined with the fact that this test is cheaper and easier, means that pre-symptomatic Alzheimer's can be tested for and found systematically. This means earlier diagnosis.
For our machine learning, we use a voted classifier of 5 separate binary classifiers: random forest, logistic regression, Gaussian naive Bayes, k-nearest neighbors, and Bernoulli naive Bayes. The voted classifier took the mode of the decisions and reported the confidence as well as the prediction. The data was 15-fold cross-validated on the feature set collected from the clinical data. We found an accuracy of 66%. However, papers have shown that it is possible to reach 96% accuracy with other types of data. With more resources and backing, we aim to work with other researchers and gather aforementioned types of data that are able to raise the accuracy to diagnostic levels.
Data sets from different clinical studies around the world were used in the machine to identify similar biomarkers in both healthy controls and Alzheimer's patients respectively. We utilized an ERP approach, commonly known as the Evoked-Related Potential Test. Specifically, we elicited the oddball paradigm test, a series of auditory low and high frequency tones, and the brain's response to each tone. Specific characteristics of waves invoked by the test, for example, the maximum peak of a certain wave commonly known as the P300, were then extracted from the data and used to create a machine learning model which could then output the probability of the patient having the disease. We hope to improve our classifier accuracy by also including resting state spectral and complexity EEG calculations such as power density analysis, spectral entropy, and many more. This is the portable EEG that is both smaller and cheaper than current Alzheimer diagnostic tools. It simply works by placing the helmet on top of your head and positioning the electrodes to their desired location. It then collects and transmits the data to a program on the computer. Let's watch it in action.
First, the patient moves to a quiet room and sits down. A technician helps put the headset on and ensures that it's positioned correctly. There are 2 ear clips that need to be attached to the earlobes. One is ground, and the other mitigates electrical noise. The patient is given headphones and is shown a computer with a loaded 2-tone oddball paradigm test. The patient presses the spacebar to start the program. He then hears a series of either standard or oddball tones separated by 900 milliseconds. The majority of the tones are a standard lower tone, while the oddball ones are less frequent higher ones. Every time the patient hears an oddball tone, they are instructed to hit the spacebar as quickly as possible. The test is complete after 200 tones are played. The computer collects the data from the EEG and the test itself, and an algorithm is run to extract relevant features from the dataset, and the machine learning program is run to diagnose the patient as Alzheimer's or healthy with a certain confidence level as mentioned before.